This episode of Real Engineering is brought to you by CuriosityStream. Sign up today and get free access to my new Logistics of D-Day series on watchnebula.com. Plane wings come in a huge variety of shapes, sizes, and configurations. We have explored how the aft swept wings of a traditional airliner and the forward swept wings of experimental planes like the X-29 affect the aerodynamic properties of the plane. We explained why modern jet fighters are designed to be aerodynamically unstable, and in one of my very first videos, we investigated why airliner manufacturers like Boeing and Airbus are installing increasingly complicated winglets at the tips of their wings. However, we have never explored in detail the theory and practice behind wing dihedral angles, which is simply the angle the wing makes with respect to a perfectly horizontal line through the base of the wing, and planes throughout history have had a huge variety of variations with this feature. From the high-mounted anhedral wing of the AV-8B Harrier, where the wing angles downwards, to the low-mounted dihedral wings of airliners and World War II era fighters, and everything in between like modern-day F-16s with low-mounted straight wings, or stranger still, the gull wings of seaplanes and inverted gull wing of the F-4U Corsair. So, what's the purpose behind all these designs? To understand this, we first have to understand the dynamic lift generated by a wing as it rolls. Let's examine a plane with dihedral wings, meaning they point upwards. In straight and level flight, the lift each wing generates does not point directly up, as the lift a wing generates is perpendicular to the aerofoil of the wing. This means the lift of the wing points inwards at an angle towards the fuselage. This seems like a strange design choice, as only the vertical component of lift contributes to getting the plane off the ground, and thus the horizontal component is wasted energy, which results in additional fuel being wasted. So why do they do it? By tilting the wings upwards, we gain roll stability, which we explored briefly in my Why Jet Fighters Can Be Too Unstable video. This means that when the plane rolls, it will naturally correct itself and return to straight and level flight with no input from the pilot. An important safety feature. This works as a result of a plane's tendency to sideslip when it rolls, meaning the plane begins to move sideways and downwards in the direction of the bank. This introduces a new airflow to the wing, which has both a vertical and sidewise component. As a result of the dihedral angle, this flow strikes the underside of the lower wing with a greater angle of attack than the higher wing, and thus the lower wing now generates more lift than the upper wing, providing a restoring force to return the plane to straight and level flight. The exact opposite occurs with anhedral wings, where the wings point downwards. Here, when sideslip occurs, the upper wing achieves more lift due to a greater angle of attack, causing the plane to roll more. High-mounted wings tend to be anhedral. Some sources will tell you that this is due to the pendulum effect, where the weight of the plane itself acts as a restoring force, like how a pendulum will naturally return to its original position when disturbed. But this is incorrect, and I nearly uploaded this explanation on Saturday before thinking about it a little harder and realizing that that didn't make any sense. The actual reason high-mounted wings are roll stable is a result of how the airflow flows around the fuselage in sideslip. With high-mounted wings, it will be deflected into the underside of the wing, increasing the lift on the lower wing and thus providing a restoring moment, while a low-mounted wing will have the airflow deflected into the top of the wing, providing a moment which will increase the roll. So, plane designers will use dihedral wings on low-mounted wings to counteract the instability of low-mounted wings, and use anhedral wings to offset the stability of high-mounted wings. We can see examples of anhedral wings in planes like the AV-8B Harrier, where the designers needed to use a high-mounted wing in order to utilize the direct thrust nozzles that would otherwise strike the top of the wing in a low-mounted wing. Perhaps the most impressive example of high-mounted anhedral wings is the Antonov AN-225, the largest plane in the world. I could not find a reference to back this up, but I assume they chose this wing configuration to increase ground clearance for its 6th turbofan engines and thus allow the plane to have extremely short landing gear, which would reduce the material needed for them and make loading procedures much easier. We also see examples of low-mounted wings with no dihedral angle at all, like the F-16. This made the F-16 slightly unstable in roll, allowing for better maneuverability. The F-16 was in fact one of the first planes in existence to deliberately introduce instability for the benefit of energy-efficient maneuvering, a technology made possible by fly-by-wire computers. Angling the wings like this does come with disadvantages. One of them is its effect on fuel economy. As stated earlier, only the vertical component of lift contributes to getting the plane off the ground, and thus the horizontal component is wasted energy, which results in additional fuel being used. But the effect is tiny. If we keep the dihedral angle relatively small, the loss in vertical lift is proportional to the cosine of the dihedral angle. A wing with a dihedral angle of 6 degrees, like a Boeing 737, will lose just 0.55% of its vertical lift in exchange for roll stability. The configurations mentioned above are the most common, but there are configurations that appear in special circumstances. The F-4 Phantom, a fighter created before fly-by-wire technology was mainstream, was found to be unstable during the testing phase, and thus they retrofitted a dihedral angle to the wingtips late in the development stage to increase roll stability. This is called a cranked dihedral. One of my favorite planes, the F-4U Corsair, features inverted gull wings, where the wings initially protrude out at an anhedral angle before sweeping back to dihedral. This wasn't for any fancy aerodynamic reason, but for a similar reason to our AN255. When the F-4U Corsair was being designed, the engineers had some design criteria they had to hit. Namely, it was required to be capable of achieving a top speed of 640 km per hour. This would require not only a large engine to achieve the power needed to overcome the immense drag at this speed, but a large propeller to provide the thrust. This created ground clearance issues for the plane that would require longer landing gear, but a longer landing gear would need to be stronger, heavier, and would take up more space. Instead, the designers decided to bring the landing gear closer to the ground by curving the wing downwards where it was located. The gull wings of seaplanes again used them for clearance reasons, as they tried to lift the wing-mounted engines clear of damaging seawater spray. These are just some examples of how dihedral angles change for different design criteria. But from here, you should be able to look at any plane and understand why it shows a particular wing dihedral or anhedral angle, like the Junkers Ju-87, another inverted gull-wing World War II era plane flown extensively by the Germans. I will be exploring many of these planes and other less examined factors that influenced the outcome of World War II in my new Logistics of D-Day series, available exclusively on Nebula, the streaming service my creator friends and I made to provide a new place to upload our content free from the shackles of the YouTube algorithm. In my debut episode, I explored the reasons Normandy was chosen as the final landing location, factoring in everything from Allied fighter plane ranges to the geology of Normandy. It's a fascinating topic that you can learn more about for just $2.99 by signing up to CuriosityStream, who are bundling our streaming service with every sign-up that uses the link in the description. With this, you'll get access to thousands of fantastic documentaries on CuriosityStream, like this one titled Pioneers in Aviation, but also get access to all my new videos completely ad-free and watch my new Nebula exclusive series. With Nebula original series, ad-free videos, downloadable episodes on iOS, with an Android app on the way, and no algorithm presenting you with endless clickbait distractions. Watch Nebula is the best place to watch your favorite educational YouTubers like Wendover Productions, Polymatter, Lessons from the Screenplay, Lindsay Ellis, Kento Bento, and much, much more. As always, thanks for watching and thank you to all my Patreon supporters. If you'd like to see more from me, the links to my Instagram, Twitter, subreddit, and Discord server are below.